Welcome to Online Algebra 2. And today we're going to be covering section 7-3, Logarithmic Functions as Inverses. Okay, so the objective for this section is to write and evaluate logarithmic expressions and to graph logarithmic functions. So if you've never seen this before, you're probably asking, what the heck is a logarithmic expression? Well, the exponential expression, y is equal to b to the x power, is 1 to 1. So its inverse is a function. So to do this, we need a new type of function. So this is pretty clear, right? If we wanted to find the inverse of this function, we would switch x and y, and we would get y by itself by taking the square root of both sides, because we understand that square and square root are two functions that undo each other. It becomes a little bit more difficult when you have an exponential function. We know this is a function, right? We can graph it. It shows us exponential growth, right? It looks kind of like that. And because it passes the vertical line test, it is a function. Because it passes the horizontal line test, it means this thing has an inverse, and that inverse is a function as well. We just need to figure out what it is. So we would switch x and y and try to solve for y. But how do I do that? Well, I could take the y root of both sides, but that wouldn't really help, because then I would just have 2 is equal to the y root of x. That doesn't really get y by itself. I could try multiplying by a fractional exponent again. That's just going to get 2 by itself. So we're going to need something new. We're going to need a new thing. And that new thing is called a logarithm. Okay? Maybe you've seen this button on your calculator, the word log. We'll talk about that in a little bit. All right, but and you probably pressed it and wasn't sure what it did. It gave you a bunch of decimals. There's all sorts of weird stuff. Okay, but a logarithm is this new function that is the inverse of an exponential function. Okay, so the logarithm of a base b of a positive number x satisfies this definition. As long as b is positive and not equal to 1, we'll talk about it in a second, the log base b of x is equal to y if and only if b to the y is equal to x. So basically, what the logarithm is doing is it's taking two numbers, and the answer to a logarithm would be the exponent that you would use to turn the base into the inside of the logarithm, right? And that's why we have this relationship right there. The way we read it is log base b of x, log base b of x. In other words, the logarithm y is the exponent to which b must be raised to get x, right? So whatever, right, the answer to a logarithm is an exponent. B must be bigger than 0, okay? Because we don't have bases for negative numbers, because that would give us imaginary results with exponents. Same thing is true with logarithms. The base can't be equal to 1, because if we plug 1 into the base, 1 to any power would always equal 1. So the answer for y would be infinite. The base is not going to be equal to 0 to either, because 0 to a power is just always going to be 0 as well. So this base right here must be bigger than 0. So it cannot be negative, it cannot be 0, and it cannot be 1. Right? And it is, the logarithm is the thing you do to a function that produces an exponent, right? So answers to logarithms are exponents. And this just explains all that a little bit more. So the exponent in the expression b to the y, it's the logarithm in the equation b log base b of x is equal to y. So the base is the same in both. So the base and the base here are both the same. In this case you're raising it to a power. In this case, you're asking yourself, what power do I need to go from there to there? Okay, and again, not equal to 1 has to be bigger than 0. So because the base is not 1, and because the base is bigger than 0, that means b to the y has to be 0. So since b to the y is the same thing as x, then x has to be bigger than 0 as well. So that means the inside of the logarithm cannot be negative either. So we can't have negatives there, we can't have negatives there. You can have negatives there. Negative exponents are okay. That is the thing, right? Gives you fractions. So log base b of x is defined only when x is bigger than 0. Okay, we'll look at a graph in a little bit. Because they are inverses of each other, their compositions go back to where you started. So if you take a base b and you raised it to the log base b of a power, you would get a. And if you took the log base b of b to the a power, you would get a as well. Basically, we are saying that the inverse of the original function of x is equal to x, and the function of the inverse function of x is equal to x. Right? So if you put something into the inverse and then or into the original function, and you take that answer and you plug it into the inverse, you go back to where you started. And that's kind of the definition of inverses, right? Undoing the other expression. Okay? So we can use the definition of a logarithm to change exponential equations and put them into logarithmic form. Okay? So here's where we're going to get started, right? So we're going to take this definition that 100 is equal to 10 squared. Right? We know that's true. Right? We're going to write it as a logarithm. Okay? So we know that log base b of x is equal to y, is equal to the exponent. Okay, so that means that the log of the base, well, that's the base, it's 10. We write that a little bit lower. Okay, we write it as a little subscript of some number is equal to the exponent. Okay, and this is special. We'll talk about that in a little bit. Okay. Next one. We write the word log, right? Just to say we know this is an exponent because of where we put it in the expression, right? We don't need a special word to say 3 exponent 4. We just know it's an exponent. Unfortunately, for logarithm, there wasn't a good symbol for logarithm, so mathematicians long ago just decided to use the word. Okay, so it's not a weird thing. It's just telling you which function we're using, right? You do this, all right? I'm telling you that's multiplication because if we write nothing in the middle there, that means multiplication. If we do x over 3, I'm telling you that's division because of the fact that we're writing it as a fraction. Okay, so the same is true for logarithm, except there's not a symbol. We have to actually write the word. Then we write the base. That's the base, right? It's the base of an exponential function. Turns into the base of my logarithm. Of a number is equal to the exponent. So log base 3 of 81 equals 4. What power do you raise 3 to give you 81? The fourth power. Let's try a few of the guided problems. This is, all right, all we're doing here, we're not solving these yet. We'll do that in a second, right? All we're doing is we're changing this expression, which uses exponents, to something that uses a logarithm. So this would be the log of 36 is equal to 2. Right, that's the base. The log base 2/3 of 8 over 27 is equal to 3. The answer to a logarithm is always an exponent. Okay? The log base 3 of 1 is equal to 0. Answers to logarithms are exponents. Okay? And so we can use the exponential form to help us evaluate certain logarithms. So if I want to evaluate this, log base 8 of 32. Well, I know the answer to a logarithm is an exponent. So I'm going to say, is there a power I can raise 8 to and just get an answer of 32? Not really. So I'm going to have to set this up as a problem. So log base 8 of 32 is equal to something. Well, let's rearrange this. And this is how we're going to solve a lot of logarithmic equations. Let's rearrange this as an exponential equation. And I can get rid of the word log by just rearranging this and saying that 8, the base, answers to logarithms are exponents, so make that an exponent, is equal to 32. Okay, well, that didn't really help me too much until I realized that both of these could be written with a power of 2. So 2 to the 5th power, whoops, that's 32. 2 to the 3rd power is equal to 2 to the 5th power. Right? 2 to the 5th power is 32. 2 to the 3rd power is 8. And now these bases are the same. These exponents must be equal to each other. And now I can divide out to 3. And so x is equal to 5 over 3. Okay? Not always that hard. These ones are a little bit easier, or one of these is a little bit easier. The first one actually is. Is there a power that raises 5? Is there something, an exponent, that 5 to that exponent gives you 125? Yeah, 5 to the 3rd power is 125. So the answer to A is 3. Unfortunately, let's just set this equal to x. 4 to some power is equal to 32. 4 to the 1st power is 4. 4 squared is 16. 4 to the 3rd is 64. So it doesn't work out perfectly. But again, I can turn this into powers of 2. And so 2x would be equal to 5. Right? That is a property. If the bases are the same, the exponents must be equal to each other. And you think about it, if I have 2 to the 5th on this side, I have to have 2 to the 5th on this side for these two to be the same thing. 2 to the 4th doesn't equal 2 to the 5th. Only 2 to the 5th equals 2 to the 5th. So that x has to be 5 over 2. So that when I multiply it by 2, I get 2 to the 5th. Here, so set that equal to x again. So 64 to some power is equal to 1 over 32. It's okay to have fractions. Fractions, these are both powers of 2. Fractions are just negative exponents. Okay, so hopefully remember that from the last chapter when we did a lot with exponents. To get a fraction, it just means a negative exponent. So that means 6x is equal to negative 5, and x is equal to negative 5 over 6. Okay. So this is a jump a little bit into how we are going to actually solve exponential equations. But for now, we can see how this works a little bit. So I said that this log was special. Okay? It is the most prevalent, the most common logarithm that we're going to use. So we can write this well, let's think about this for a second. This is the most common root. It's a square root. I don't write a 2 there. Could be weird. For logarithms that are, or for roots that are not 2, I have to write 3 or I have to write 4. Okay? But for the most common one, I write it just like that in order to save time. This is the most common logarithm, the base 10 logarithm, because base 10 is the most common base in our number system. right? Every digit is a power of 10, right? We have scientific notation that deals with powers of 10, right? Powers of 10 is how our number system works. So this is the most common logarithm, so I can rewrite it without actually showing the x. So that means if you don't see the x, if you don't see a base, you must assume it is a 10. There's one more special logarithm that we'll get to in a later section, okay, with the second most common base. All right, but now let's just stick with the common logarithm. Okay, so many measures of physical phenomena have a wide range of values that the reported measurements are logarithms, exponents of the values. That is, they are a logarithmic scale. One of them is the Richter scale. Another is the decibels, a scale that measures sound. Richter scale measures the magnitude of earthquakes. And there are a few others, okay? But these are the most common. So when you say an earthquake has a magnitude of 3 or 4, it means that the magnitude 4 is 30 times more powerful than the one scale lower. Okay, so this is a logarithmic scale. Each increase in one is an order of magnitude bigger than the other ones. Okay, so let's try a problem with this. 2004, an earthquake with a magnitude of 9.3 on the Richter scale hit off the northwest coast of Sumatra. Diagram shows the magnitude of an earthquake, 8.7, that hit in 2005. This formula, log of intensity 1 over intensity 2 is equal to the measure 1 minus the measure 2. Compares the intensity levels of earthquake where I is the intensity level determined by a seismograph and M is the Richter scale. So how much more intense was this? So this one was 8.7, that one was 9.3. It doesn't seem like it's that much more intense, but let's actually solve this equation and figure out how much more intense that actually is, the bigger one. So this ratio is going to be equal to 9.3 minus 8.7. Okay. And we get that the log of this ratio is going to be 0.6. So I don't really want to solve for each one of these. I just want the ratio, right? I want to know how much more intense the one is than the other. So I can rewrite this as an exponential equation. I just need to know the base, that number right there that I don't see. And if I don't see it, it means it's a 10. Answers to logarithms are exponents, and that is going to equal my ratio right here. So now you're going to need a calculator. Plug that into a calculator, and you get this ratio is about 4. Okay, so that means that that a 9.3 is 4 times more powerful than an 8.7. So that doesn't seem that much of a difference, but it does make a big difference. Let's graph these things, okay? So because the logarithmic function is the inverse of an exponential function, this is a graph of y is equal to 10 to the x power. This is the graph of y is equal to the log base 10 of x, right? I don't have to say base 10. I just say log x, okay? Knowing that it's a base 10. Notice that these two are reflections of each other across the line y is equal to x. So if this has a coordinate 0, 1, this one has a coordinate 1, 0. Plug a 1 into this, you get a 10. Plug a 10 into this, you get a 1. Okay? Because remember, answers to logarithms are exponents. So that gives us two ways to graph these things. So if I have a logarithm, I could always graph the exponential function and flip it over, or I could plug things into the logarithm that make sense, just like I did for square roots. So if you want to graph this, log base 3 of x, describe the domain and range, identify intercept, asymptotes, all that stuff. going to make a table. Okay, so one technique would be to change this to an exponential function. Okay, so we could say that, rewrite this as 3 to the x power, let's not use x. We could say that 3 to the y power is equal to x, and then I could just reverse these and switch them to give me my inverse. And then switch them back after I graph it. But that seems like a lot. So I would rather just plug in numbers that work well. You cannot take the logarithm of 0. Remember our rules is that my base, or my number in here can't be 0. So this doesn't work. That number in there can't be negative. It doesn't work. Okay, so that x has to be, the input has to be greater than or equal, or sorry, greater than 0, just not equal to 0. I plug in fractions that are less than 1. 1 doesn't have to be my starting point, but I can't plug in any negative numbers or 0. So let's plug in numbers that work well first, like 1. What exponent, what can you put in there and have the answer be 1? And that's a 0. Okay. 3 to the 0 power is equal to 1. Well, this seems like a bad idea. What power do you put there? What power do you put in there and get an answer of 2? I don't know. Weird decimal. Weird, somewhere in between 1 and 2. I don't want that. Oops. But I do want this. Because 3 to the first power is equal to 3. Okay, so you see what I'm doing here is I'm saying if this was a 3, what power do I need to go from here to here? What power do I need to go from 3 to 9? What power do I need to go from 3 to 27? Notice how far this goes. And the next one's 81. Okay, but also we can think about fractions. So to go from 3 and have an answer be negative 1/3, sorry, 1/3, I would need an exponent of negative 1. 1/9 would have an exponent of negative 2. 1/27 would have an exponent of negative 3. So hopefully you see the pattern here. As I get really, really close, well, let's just graph these. 1, 0, 3, 1, 9, 2, 27, 3. But as I go closer and closer to the y-axis, right, 1/3 was negative 1, 1/9, which is even closer, that's like 2/3, 1/3, 1/9, 1/27, 1/81st, right? You're going to get closer and closer and closer to the y-axis, but you're never actually going to cross because we're not allowed to plug negative numbers into logarithms. If you try it on your calculator, take the log of negative 1. It's going to give you an error. Okay? So this graph is never going to cross the y-axis, and it then is going to start going up very slowly, but still going up. Okay? So that means the domain of this function, the domain is from 0, not including 0, to infinity. And the range, well, it goes all the way down. It's going up really slowly, but it's still going up. So the range is from negative infinity to positive infinity. This function has no y-intercept. It has an x-intercept at 1, 0. And we can do this for any logarithmic function. Pick numbers that work well inside of the logarithm. I have another one? Yeah. So you want to graph this. So y is equal to log 4 of x. Pick numbers that work well with 4. Well, remember, output, the y-coordinate is going to be the exponent. Right? Answers to logarithms are exponents. So if x is 1, the exponent is 0. 4 to the 0 power is equal to 1. If x is 4, the exponent is 1. 16 would be 2. And then 64, which is way off of here, is 3. And a quarter would be negative 1. A 16th, a 64th, and same pattern is we're gonna start going. Okay, and there's my graph. A vertical asymptote, a line that the graph does not cross, but gets very, very close to on the y-axis. I suppose you use the following table to help you graph. Y is equal to the log base 2 of x. So if this is x, and you're thinking about this, you can easily get the y's. So what power does this? And the answer is nothing. What power does this? Nothing. Oh, this does a power. That's 0 power. And first power. Okay. So just remember that it is not possible to raise 2 to some exponential power and then get a negative number. Just think of the graph of 2. Think of this graph, 2 to the x power. It looks like that. No negative numbers in there, right? There's negative inputs, but there's no outputs. There's no way that you got down to there. There's no way that this output of an exponential function was a negative. Okay. We can do transformations on these just like we did with every other function. So y is equal to log b of x is the parent for any function family. That number can change. Okay. You can graph all the transformations, log base b of x minus h plus k. I'm moving the graph up, down, left, right, stretch, compress, reflect. Here's our transformations, right? This number in the front there, a. If it is bigger than 1, it's a stretch. Stretches the function vertically. If it is a fraction between 0 and 1, it compresses the function vertically. If it is a negative number, it reflects in the x-axis. No negative numbers inside, but we can have a negative number in the front. Left or right, up and down, everything together. Okay. So the same transformations that we did for other functions, we can do for this one. So I don't want to graph these whole things, but let's just talk about what this means. The 4 is the base. That's the parent function. So basically, we are saying, how does this function compare to something with no transformations, log base 4 of x? And basically, the only difference is now it's gone right 3, up 4. Okay. So those transformations, if you do want to graph this, plug up Desmos and take a look, and you could see that the functions have a very similar shape. They've just been moved to a different spot. This, right 3, up 4. Part B, stretched by a factor of 5. So instead of looking kind of like this, and it would still kind of look like this, it would just be going up much, much faster. And they would cross at the same spot, right? But instead of having an output of 1, it would have an output of 5. And having an output of 2, it would have an output of 10. So this slope, or this curve, would get much, much bigger. Okay? So let's play around with finding the inverse. Okay, remember our method to finding the inverse. It was called the switch and solve strategy. So my first step was to switch x and y. Now I have to get y by itself. And because y is inside of the logarithm, the first thing I have to do is change this back to an exponential function. Get rid of the word logarithm. And so the way I can do that is by by rewriting this as an exponential function. That is my base. The answer to the logarithm is an exponent, and it equals what is inside. And so now I can very clearly have y by itself like that. Okay? And we could go back the other way by switching x and y, isolating this term, and now rewriting this as a logarithm, because we would say the log base 4 of whatever this is equal to the exponent. Okay? So that's sort of the idea of the way that you would take a logarithm and take its inverse by changing it to a exponential function, something with a variable in the exponent, and an exponential function and changing it back to a logarithm using inverses. These two functions are inverses of each other. All right, so quick overview. Hopefully we don't have any troubles with 1 through 4. Evaluate each logarithm 2 to the 8th power. That's a nice one. That is 3. That is 2. 7 squared is 49. 9, that's 1. And that is a negative 2. Log base 2 of 1/4 is a negative 2. You change a number to a fraction with negative exponents. Common logarithm. That means it has a base 10. No. Yes. Yes. Don't write it that way. No. Okay. We would write this as log of 100, which would be 2. And how could you use inverses to graph this? Well, you could graph 6 to the y power instead. I would rather just use numbers that work well with the base of 6. Like if I was going to input numbers for x, it would be 1, and I would get an answer of 0. It would be 6. It would be 36, right? Because what power do you raise 6 to get 36? The answer is 2. And how do these two graphs compare? This graph is shifted to the left 4. How are they different? Well, graph them and take a look. All right, so that was 7-3, logarithmic functions as inverses.